These are the answers to the Chapter 4 and 5 practice quiz. And we'll start with the multiple choice questions. So here's number 1. Your job is to arrange the ions in order of increasing concentration. Let's take a look at the numbers that we have. We know that volume in liters multiplied by molarity equals moles. So we have 0.1 liter of a solution of sodium sulfate that has a concentration of 0.2 moles per liter. Again, this is math without a calculator, so we end up with 0.02 moles of sodium sulfate. We do the same calculation, multiplying 0.1 by 0.5, and we get 0.05 moles of potassium sulfate. Remember that there are 2 moles of sodium for every 1 mole of sodium sulfate. So the actual number of moles of sodium is 0.04. The number of moles of sulfate is going to be added from the 2 solutions. So we have 0.02 moles of sulfate from the 1 volume. In the other solution, we multiply 0.05 times 2 because there are 2 potassium ions per mole, and we have 0.05 moles of sulfate. So we're adding the sulfate together. To put all of this together, the smallest number of moles is going to have the lowest concentration. That's going to be sodium. So sodium is the lowest. 0.02 plus 0.05 is 0.07. So sulfate comes next. And then finally, potassium has the highest concentration. So the correct answer to this question is B. In number 2, we're going to convert grams of calcium chloride into moles. The number is fairly easy for us to do here. It's mental math. You can take 11 grams and convert that into moles by dividing by 111. So that means that the number of moles of calcium chloride would be 1/10, or 0.1. We are going to dissolve that calcium chloride in 500 milliliters, and that volume in liters is 0.5. So here is the math we're doing to calculate the concentration of calcium chloride. 0.1 divided by 0.5 is equal to 0.2. Now before you circle B as the correct answer, remember that the question said, what is the concentration of chloride ions? And that will be twice as much as the concentration of calcium chloride itself. So the correct answer is D. Number 3 is asking us to calculate the number of grams of glucose. We know that we have 500 milliliters, that would be 0.5 liters. Multiply that by the concentration, so 0.5 times 0.5, and we get 0.25 moles, or 1/4 of a mole of glucose. So now all we have to do is take 1/4 of the number 180, and so therefore we get 45 for our answer. Number 3 is B. This question is asking us how many milliliters of a 10 molar stock solution of hydrochloric acid are needed to prepare 250 milliliters of a 0.1 molar solution. So we're going to use the equation m times v equals m times v. We'll plug in everything we know. So 10, which is the concentration of the stock solution, times the volume in milliliters, we don't know what that is yet, equals 0.1, the concentration of the dilute solution, times its volume, 250 milliliters. Pretty simple math. 0.1 times 250 is 25, and 25 divided by 10 is 2.5. So correct answer is B. Number 5, they don't give us a balanced chemical equation, so we should write one. It's between nitric acid and calcium hydroxide. The products are water and calcium nitrate. But it's very important you recognize that there is a 2-to-1 ratio between moles of nitric acid and moles of calcium hydroxide. If we have 0.5 moles of calcium hydroxide, then we're going to need twice as much in terms of moles. We need 1 mole of nitric acid. So where is that 1 mole of nitric acid coming from? It's coming from a solution which is 2 moles per liter. Let's put moles of nitric acid on the bottom and either 1 liter or 1,000 milliliters on top. Again, this is pretty simple mental math. 1,000 divided by 2 is 500. So correct answer is C. In number 6, we've seen a problem like this before where you have a titration and you're trying to figure out the molar mass of the monoprotic acid HX. If it's a monoprotic acid, that means there's a 1-to-1 mole ratio between the acid and sodium hydroxide. The moles of sodium hydroxide can be calculated by doing volume times molarity. Again, pretty simple mental math, 0.02 liters times 0.1 moles per liter. We have 0.002 moles of the base, sodium hydroxide. Because of the 1-to-1 mole ratio, we have 0.002 moles of the acid. And since mass divided by moles will give us the molar mass, we're doing 0.5 divided by 0.002. If this mental math seems too challenging, let's multiply the top and the bottom by 1,000. Let's move the decimal 3 spaces to the right. So now this ratio becomes 500 over 2, and the correct answer is 250 grams per mole, which is C. All right, this is question 7. We have to choose which combination of solutions would produce the greatest mass of silver chloride. Let's analyze this question from the perspective of how many moles of silver do we have, how many moles of chloride do we have, and how many moles of silver chloride can we make. If we do volume times molarity, that would be 0.1 liters times 0.1 moles per liter. So in choice A, we have 0.01 moles of both silver and chloride. And that's how many moles of silver chloride we could make. In choice B, we have the same number of moles of silver, but we have 0.04 moles of chloride. This doesn't increase our yield because the silver is still the limiting reactant. For part C, we now have a greater concentration of silver nitrate. So now we have 0.02 moles of silver, and we have 0.02 moles of chloride because it's calcium chloride, so therefore we get to multiply the moles of calcium chloride by 2. So that's a greater number of moles. And then for part D, even though we have a greater concentration of silver nitrate and a larger number of moles of silver ions, the limiting reactant is the chloride ion. So we can only produce 0.01 moles of silver chloride. The correct answer to this question is C. All right, number 8 is asking us to figure out which of the following calculations is set up correctly to determine the mass percentage of iodide in this Ki tablet. So the mass percentage of iodide would be the mass of iodide divided by the mass of the tablet times 100. So where is the mass of iodide going to come from? It's going to come from the mass of the precipitate, which is PbI2, lead iodide. Let's first convert from grams to moles, and the periodic table can tell us that PbI2 has a molar mass of 461. Then we have to convert from moles of lead iodide to just moles of iodide, and there's a 2-to-1 ratio based on that calculation. And then finally, to go back to grams of iodide, the periodic table tells us that the molar mass of iodine is 126.9. Now let's look at the 4 choices and see which ones we can eliminate. There's supposed to be a 2 in the calculation, so it cannot be A. The 2 should be on the top because we're multiplying, so it can't be B. And there's no 2 at all mentioned in choice D. So correct answer, based on the calculation that we did, is C. Question 9 is dealing with thermochemistry. We have work being done by the surroundings on the system, and we have heat being transferred from the system to the surroundings. Delta E is equal to the sum of the heat and the work. The heat is going to be negative 500 because the system is losing heat. The work is going to be positive 200 because it's being done on the system, and that sum is negative 300. So based on those signs, correct answer to number 9 is B. In number 10, we have the same equation where delta E equals Q plus W. We're looking for conditions in which the sign of delta E will always be positive. So for Q to be positive, the heat must be absorbed by the system. For W to be positive, work must be done on the system. So correct answer to number 10 is A. In number 11, we have a combination of arrows. So Q is heat and W is work. Let's take a look at these 4 diagrams. Remember that an endothermic process is which heat is absorbed, so flowing into the system from the surroundings, and an exothermic process, heat is released or exiting the system. Endothermic and exothermic is only focused on heat. This has nothing to do with work or delta E. So the word endothermic is just about heat, not about work. Process 1 represents an exothermic process because heat is exiting the system. Process 2 is an endothermic process. And in process 3, the delta E would be positive. And in process 4, work is being done by the system on the surroundings. So therefore, correct answer to number 11 is B. Process 2 is endothermic because all we care about is heat, which is Q. Number 12 asks you to decide if the potential energy is going to increase or decrease, and we justify it talking about the attraction between the particles. So these particles have opposite charge. If you take a look on page 161, you'll see a diagram in which it's showing opposite charges being moved closer together, and the potential energy decreases as the particles are becoming more attracted to each other. So potential energy decreases because the attraction increases. In number 13, it's talking about potassium chlorate, which is KClO3, decomposing into potassium chloride, KCl, and oxygen. This reaction is an endothermic process because heat is absorbed to convert potassium chlorate into the products. If the sign of delta H is positive for an endothermic reaction, that means that the enthalpy of the products are higher than the enthalpy of the reactants. So we can eliminate choices B and D because the delta H has the wrong sign. We can eliminate choice A because it should show the products at a higher enthalpy level than the reactants. So correct answer for number 13 is C. Number 14 gives us a thermochemical equation involving the synthesis of ammonia from its elements, and that's an exothermic reaction. We know that heat is released. Our job is to figure out how many grams of ammonia are produced when 875 joules of heat is released. Let's first convert from joules to kilojoules, and then we can convert from kilojoules into moles. So 92.4 kilojoules of heat are released for every 2 moles of ammonia produced. The molar mass of ammonia is about 17 grams. So based on these numbers, 1,000 has to be on the bottom, so it cannot be either C or D, and 2 needs to go on top, 92.4 on the bottom. So correct answer to number 14 is B. Number 15 involves a sample of dry ice that is in a rigid metal container, and it is being heated because it starts out at negative 100 degrees and it warms up to room temperature 25. Let's talk about work for this particular process. It's a rigid metal container. If the gas caused a piston to move, like the diagram on page 170, we would assume that work is being done by the system on the surroundings. And the delta V would be the change in volume. But what if the system does not change its volume during the course of a process? Does it do pressure volume work? And the answer is no. If delta V is equal to 0, then no work is done. Here we have a rigid metal container. There's no change in volume, so no work is done. The correct answer is either A or B. We said that it's going to absorb heat as it changes from minus 100 Celsius to 25 Celsius. So therefore, if it's absorbing heat, Q should be positive. Correct answer is A. This question shows us that when you start with aqueous ions, magnesium and sulfate, and you end with solid magnesium sulfate, that thermochemical equation has a positive 96 kilojoules associated with it. That's an endothermic process. However, dissolving solid magnesium sulfate in water would be the opposite of the reaction shown. So dissolving solid magnesium sulfate in water is actually an exothermic process. It'd be negative 96 kilojoules. If it's an exothermic process, heat will be released by the system, and if that's the case, dissolving the magnesium sulfate into the water will release heat to the surroundings. Water is considered to be part of the surroundings. The temperature of the water would increase. Correct answer is B. All right, on to the free response questions. Number 1, a chemistry teacher needs to prepare a silver nitrate solution for a lab experiment. We have to calculate the mass of solid silver nitrate that is needed to prepare 500 milliliters, which is 0.5 liters, of a 0.110 moles per liter solution. So if I do this calculation from volume times molarity, I can get moles. Let's go ahead and finish this problem off by calculating the number of grams. And that 169.88 just comes from the molar mass of silver nitrate. Our answer, rounded off to 3 significant figures based on the molarity, is 9.34. In part B of this question, we have to write a balanced equation. First a molecular equation, then a net ionic equation. This is a redox reaction in which zinc is being oxidized and silver is being reduced. We start with just zinc metal with no charge, silver nitrate, AgNO3. Zinc has a charge of +2 on its ions, so there's the formula for zinc nitrate, and then silver metal. We'll go ahead and stick in the coefficients, a 2 next to the silver nitrate and the silver. The net ionic equation will eliminate the spectator ions, which are nitrate ions. We still have zinc, but now we have silver ions, zinc ions, and silver. And again, we can balance it in the same way. When we do the limiting reactant calculation, we can start with 1.50 grams of zinc, and we can convert that to volume of silver nitrate solution. So first we're going to go from grams to moles based on the molar mass of zinc. Remember, there was a 2-to-1 mole ratio between silver nitrate and zinc in the balanced equation. And then the volume of the solution would be calculated by using molarity as a conversion factor. 0.110 moles of silver nitrate for every 1 liter or 1,000 milliliters. If we do this calculation, it turns out that we need 417 milliliters of this silver nitrate solution, but we only have 250 milliliters available. So that's going to prove that silver nitrate is the limiting reactant. Another way you could have done this is to start with 250 milliliters of silver nitrate. First, convert that from volume to moles using molarity as a conversion factor. Again, remembering the 2-to-1 ratio between silver nitrate and zinc. Finally, convert to grams of zinc using the periodic table. We discovered that we need 0.899 grams of zinc. Since we have 1.5 grams of zinc, zinc is present in an excess amount because we have more available than we need, but silver nitrate is the limiting reactant because we need more than we have available. So now that we've established that silver nitrate is the limiting reactant, we can calculate the concentration of zinc ions that are present in the solution after the reaction is complete. Since all of the silver nitrate reacts, let's convert 250 milliliters of silver nitrate solution into moles, and let's convert that into moles of zinc. At that point, we get 0.01375 moles of zinc that reacted and has given us that number of zinc ions. So with a concentration, moles divided by liters, the total volume would be 250 milliliters, or 0.250 liters. Our concentration of zinc ions at the end of the reaction is 0.0550. Another way you could have done this calculation, an even simpler calculation, would have been to say, all right, we had 0.11 moles per liter of silver. All of that reacts. And because of the 1:2 ratio, the concentration of zinc should be half as much as the initial concentration of silver. So 0.110 divided by 2 would have actually given you the correct answer to this question in a little simpler way. Hopefully that calculation makes sense to you. Okay, second free response question. A chemistry teacher needs to prepare a hydrochloric acid solution. We have 6 molar hydrochloric acid for our stock solution, and we're trying to make a dilute solution of 0.10 molar. Let's go ahead and do the M times V equation. The concentrated solution was 6.0. The dilute solution was 0.10. The volume of the dilute solution is 500 milliliters. So we're going to be doing the math of 0.1 times 500, which is 50, divided by 6, rounding that off to 2 significant figures based on the measurements we're given. 8.3 milliliters of the stock solution is needed. In part B, they're telling us that after the 2 solutions were mixed, the temperature increased immediately. So therefore, since the water is considered to be part of the surroundings, if the temperature of the solution is increasing, it must be an exothermic reaction because heat is released. And again, the thermometer is part of the surroundings. In this part of the question, we are given that 279 joules of heat was associated with the chemicals that reacted in this experiment. Let's remind ourselves of the balanced chemical equation between hydrochloric acid and sodium hydroxide. We know that we have 50 milliliters of a 0.1 molar solution of each reactant. And we know that if we calculate volume times molarity, so 0.050 liters times 0.1, we get 0.0050 moles of either HCl or NaOH. The delta H is 279 joules. That's going to be written as a negative number because it's exothermic, divided by the moles of either the acid or the base. We can use either one because it's a 1-to-1 ratio and there is no limiting reactant. They both are equally going to produce the same number of moles. So 0.005 moles. If we do this math and we calculate the value of delta H in units of kilojoules per mole, we get negative 56 kilojoules per mole for this neutralization reaction. Now we have to fill in the missing information in an enthalpy diagram. We know that the overall equation is HCl plus NaOH to produce water and sodium chloride. Because it is an exothermic reaction, the enthalpy of the reactants should be at a higher level than the enthalpy of the products. So we're going downhill from top to bottom, and so we show the arrow indicating the direction of the reaction from reactants to products. Now this question is asking what would happen if we carried out the experiment, but this time using 0.2 molar concentration of solution instead of 0.1 molar. Would the magnitude of Q be less than, more than, or equal to 279 joules? Well, the magnitude of Q would be greater than 279. That's because we're using twice as much moles of reactants. So the magnitude of Q is directly proportional to the amount or moles of the reactants. And since the number of moles has been doubled, the amount of heat would also be doubled. Would the magnitude of delta H be less than, more than, or equal to? This time the magnitude of delta H would be equal to the value that we had obtained earlier, the negative 56 kilojoules per mole. We would still get that same number because both Q and moles have been increased proportionately, they've been doubled, so therefore the ratio of kilojoules divided by moles for this experiment would still give us the same value. Okay, well that wraps up the answers and explanations to the practice quiz. I hope that was helpful to you. Good luck studying. Thanks for watching.